Welcome, everyone. I would like to thank everyone of you for coming for my talk, because it's the last one today, and it's Sunday, and we all want to go home. So thank you for coming. My name is Tovbin. I work at Salesforce, and we're building a machine learning platform named Einstein. And my talk will be a lot about machine learning today and a lot about Scala, so it's kind of an intersection of both worlds. And I think it will be interesting for any of you. I think every presentation should have something beautiful in it. So mine has this beautiful quote. And I took also one line out of it, put as a title, "Thou truth to be a liar." So no matter what you do, actually it has nothing to do with my presentation. I just like Shakespeare. And I read it in Russian. So when I started reading in English, I said, oh, this is even better. So what I'm going to talk about is I'm going to give you a short introduction to machine learning. Whoever of you know it, will be great to repeat it. Whoever doesn't, you'll get some new stuff to learn. Then I'm going to talk about real-life machine learning and the challenges that we have. The next topic would be how we build an application using SparkML. And MLlib, it doesn't matter, they have this rename issue, right? We don't know what's exactly it's called right now. Then we're gonna dive into the type feature engineering that you might have heard from my colleague earlier today, Shubha Nabar, who gave you a short introduction in how we do it at Salesforce using SparkMLlib and our own in-house transformation library we call Optimus Prime. Then we're going to talk about the behind the scenes, about some cool and neat stuff we did to make it all happen. And I think you will find it beautiful as I do as a software engineer. And at the end, I'm going to show you some summary and what is the perspectives of this project going forward. So what is machine learning? Machine learning is an ability of computer to learn. When we build an algorithm, when we build a program, we wanted to be able to have an ability to learn from the data or an experience, right? Experience is just the data. So we want to feed in more data and get some different behavior of the algorithm that we have. And what are the tasks machine learning solves? Well, we have a lot of tasks around the world we already know that are solved by machine learning, and we are introducing more and more fields that we apply machine learning to, such as diagnosis, prediction, data mining, and so on. So how does it usually look from a user perspective to build a machine learning model? So we have a bunch of data that we get, some raw data, maybe some sensor data, or I don't know, user clicks, or something that we want to observe on. Then we develop some features out of it. So when we say feature engineering in machine learning terms, it means we want to define certain properties of the data that are important for us. Those properties should be independent and properly distributed. Otherwise, we cannot even trust the predictions we do. Once we do the feature engineers, and actually this is one of the most complicated processes because it might include aggregations and joins of data, computing distributions. It might take a lot of compute power and a lot of human resources just to pick which properties of the data to model on. So we want to make this process to be as reliable as possible, as fast as possible, and as convenient as possible for engineers. Then we feed it into the model training. Model training is the part of the machine learning system where we apply algorithms on the features that we produced. For example, logistic regression, or random forest, or you name it, word to vec. We usually want to prepare the data in the way algorithm wants it. So if it's a logistic regression, we want to give it a numerical vector. So we want to transform all our features that we engineered into some numerics and some doubles or whatever. Once the model training completes, we get a bunch of models. Those models are being used for predictions. This is actually what we want at the end of the day. We want to pick the best model, and that's where the next step comes out. This is the model evaluation. On the model evaluation, we compare multiple models one to each other based on some golden standard, or maybe some predefined threshold, or something dynamic. So this is all in theory. This is what we read in the books when we read about machine learning. What's in real life we see, it's actually a bit more complicated. It's rather building a pipeline, not a model. So we're talking about multiple data sources where we feed, which all of them has, or some of them might have different data formats, I would say different cadences of data. Some of the data might be streamed, some of the data might be in the flat files, some might be in the snapshots of the databases. We do want to make some sense of this data. That's why we need an extra step. We need an ETL step. We all know what ETL is, so I'm not going to elaborate on that. ETL may be as complex as it may be very complex. We might have multiple aggregations. In a step, we want to have some filtering. We want to join some data, clean it up, and so on. Then we do feature engineering, as I mentioned, model training, and then we produce models. Again, do an evaluation. Well, evaluation actually can discard some models when it produces it. Okay, this model is not good. We need to retrain the model because, I don't know, there was a bug. Or it's a sanity checker says this model provides bad predictions or something else. Or there are not enough features. We just suddenly get bad results in the model predictions because there is not enough features. So we need to add some more features or redo some distributions. Once the evaluation is satisfied with the model quality, the model goes to production. We deploy it to some web server or, I don't know, in the backend system. This binary becomes productionized, and then we start scoring new items with it. So this is the scoring part. Well, actually, for scoring, we also need to get the feature engineered step as well. So every new record that we want to score, meaning that we want to provide a prediction for, needs to become into the same format as model does. So that's why we actually have that. Once the scoring is completed, we have the happy user. Wow, yay, we got the scores back. Well, actually, the score results can also become new features, and then this loop can go on. So if I predicted certain, say, a likelihood for the lead to convert, this also can become a property of new coming models. They can base their feature engineering based on that fields. So that's why it's kind of all circular here. So real FML, I'm just going to want to mention some problems. This list is by no means as exhaustive. So ETL is really tough. We all know that. Read Wikipedia, read papers on this, read books. We're doing it for a while already. Feature engineering is even tougher because it's on top of the data that we combined and aggregated and everything. Now we want to make it into the form that our mathematical algorithms can run on. And then next one, actually like it a lot. So our prototype in R, Python, blah, blah, runs great. But when we deploy it, anything can happen. You mistyped it, you mischecked it, something bad with the code. It doesn't scale. It's like, come on. Things just don't work because your sample ran on 2,000 lines of data. Copy-pasting code basically doesn't work as well, right? We don't want to copy-paste code into the Git, into the GIST, and then share between teams. And like, oh, look, I have this new feature I just did. I need a new model. You want to try that? Yeah, I'm going to try that. And then it's we don't want to lose it. We actually want to track all those things. So we want it to be part of the code base. Model training fails exactly 2 hours after you go to sleep. Happens all the time. Like, actually all the time. You run something, it fails, you come next day, what was I doing yesterday? Maybe I'm going to repeat it, and then just, days go by, weeks go by, and nothing. So that's bad. We don't want to have that. And then different problems, right? Data is not there, data is there, different format, out of memory, insufficient space, our jobs failing because we didn't do something. And then, of course, serialization errors. So who guys never seen serialization errors? Like everyone's seen serialization. Well, yes. You start up Spark, you get serialization error. Oh, you forgot to whatever cryo thing. So now we have models and scores, but can we trust them? That's a huge question. Like, can we trust the machine? I don't trust the machine. Don't tell anyone though. So specifically for Salesforce, we have more stuff, but I just named kind of the multi-fun part. The multi-tenancy problem for Salesforce. We, as a platform, build models for all the customers. So we have Square, we have Fanatics, we have thousands more customers on our platform. It's not like we're part of a company that we have our own data science team and we build 5 models to do, I don't know, churn prediction, and we're done. So no, we are customizing it for all the customers. And then we have environments. So we need to maintain, our production maintains live staging, QA, and dev for all the customers. And then we have data sources. So this is just internal ones, I mean, like Marketing Cloud, Service Cloud. But there can be some external ones. So we want to inject Twitter streams for our users. How do you do that? There are companies doing that, actually. Or multiple data entities, such as leads, opportunities, or anything else. On top of that, we're building multiple applications. So we want to do lead scoring. We want to sort our leads based on the likelihood to convert within the next 3 days or 3 weeks. That's really interesting. How do we do that? Difficult, because all leads are different based on the customer. The domains are different. Things are actually different. How do we make them work the same? That's the biggest challenge for us. How do we scale the machine learning capabilities that our team has across the company? We don't want to replicate our team. So, and then we have other verticals or dimensions, I would say, such as security. So we want to, for example, have our data encrypted and only decrypted when we model it. We want to be able to scale no matter how many records you have, just by adding machines, automate the processes, of course, right? Transparency for the users and cost efficiency and so on. So that's why we built Salesforce Einstein. This is like the best slide for me. I love it because it has so many logos. I like logos. You see this? It's from Fallout. Whoever is in theme will recognize. So AI for everyone. That's our kind of motto. We want to do artificial intelligence for everyone on the planet, but we're starting humble. We do it only for Salesforce. So machine learning for customers, engineers, and data scientists, whoever, you name it. So we're just gonna ship it and then see what happens with it. We aim to not have any ETL. So kind of ETL easy pipeline. So you just have the data. It's there. You don't have to worry about this. And no PhD. Read the tutorial and move on. So we started acquiring great pieces into our stack. So first of all, we said we need some typed language. So we picked Scala. We're going to do Scala. And then we started looking into the great fits for our machine learning. So we picked Spark and we run on Amazon. And we use DCOS to Dockerize everything. We also have Prediction.io. We are lucky to have them as part of our team, and we are pushing their project further. So whoever using it, it's great. It's going to be there for a long time. Now it's a part of Apache Incubator. It's going to be top-level project soon. And we have our own in-house, Optimus Prime. This is the one I'm going to be talking for the rest of my talk. I'm going to give you a lot of cool stuff about it, and I hope we're going to open source it at some point. So it's a transformation framework. That's why it's called Optimus Prime. I mean, everybody got it already. It's declarative. It's collaborative because we can share actually code. We can share libraries. It's reusable because it's built like this. We just built it to be reusable, built it in pieces. And it's, of course, typed. We're trying to have types all across the stack. We also have services. Microservices, nanoservices, septo services, I don't know, Google, smaller services for different pieces of our platform that we do for scheduling and monitoring and authentication, authorization, a lot of pieces that we have. I'm going to concentrate mainly on machine learning aspect right now and on Optimus Prime. So let's start from showing how we do a machine learning application with Spark ML lib or ML. I'm not close on the name now because I think it's ML. So say we want to predict survival on Titanic. This is a very famous data set. Whoever did any Kaggle training and who didn't should do that. That's like a new hacker rank for data scientists. So what are the fields that actually influenced the survival? So I'm basing the sample on this GitHub example from Ben, which did a great job. So building Spark application starts from a bunch of imports and spin up Spark. In the local mode, everyone sees this? That's awesome. I made it like bold enough. I heard there are problems with projectors. So spin up Spark, and then you implicit something from the context further on, right? So you can reuse this context down the line. And then, whoa, we start by defining schema. A bit scary, not that bad. I just defined, this is a helper function, read data, and it defines a schema that says, okay, these are the fields I want to get from the CSV file, and their types are integer or double or string or whatever type I want. And then I'm saying if it's nullable or not. So I set everything to nullable just in case, because I don't know what's in there. Very easy to misspell fields. Well, let's hope I didn't. So I kind of double check with my CSV file multiple times. Great. And then you can set any type there. And then what happens is just going to explode in runtime. Well, I don't care. Let's care about this later. So we create a data frame by reading the data. And then actually doing some renames on the field, so they will be lowercased. And there is no better way. I mean, maybe there is a better way. I'm just doing one by one. And I'm only picking actually the fields I want to be in my model. I don't care about the rest. I'm taking the survived field. I'm taking the gender field, age, passenger class, siblings, spouses. This is the number of siblings and spouses that the person has. Parish is parent and children, and then embarked, which station the person embarked. At the end of this thing, I'm reading the data from the Titanic CSV file, and I'm getting my data in data frame. So whoever you're familiar with Spark data frame is untyped metrics of values, or basically maybe just a set of rows. And each row is just map. It's typed, but it's typed at runtime. So now I want to do some feature engineering, right? A little bit. I want to modify my data a little bit so it will help me to do my machine learning. So I made this function add features. So I want to create a new column, family size. So what is the family size? Sum of siblings, spouses plus the parents, children, and myself. And I'm modifying the data frame. This is how you modify a data frame in Spark. You do it with column. You pass the new column name as a string. You pass your UDF, user-defined function, and then you pass columns. You also name them by names. I can do whatever I want here. I can override columns. So basically, you think about it, right? I have two functions now, next function, and I can override the same column my previous function did. Nobody will do anything about it, because I can. I'm just going to do that. And it happens when you have multiple teams working on the same data set. And then this function, for example, fills the missing data. So whatever data is missing, if age is null, I want to replace it with some average. So first I need to compute the average, and then I'm replacing the average with this field. And then I'm doing something for the station. So if the station is missing, I'm replacing with the default Southampton station. Okay, done with this. Now I'm actually modifying the data. Okay, modify the data, field missing, but first I need to do the add features. And then I need to remember to cache it, and then unpersist it maybe, because it's Spark. Whoever you work with Spark knows that it needs to use, you want to use the cache, because everything is lazy. So you want to cache stuff, but you need to cache wisely, not to over-cache, because it's going to start writing to disk. And if you don't want it to be writing to disk, you need to use different storage, blah, blah. It's a long story. And it's interviews with your code. So when I code now, data scientist needs to remember to do those things. It's basically not happening. Usually what happens, they have the data scientist and maybe some other team productionizing your code later. And then I'm splitting the data into my test set and the train set. I'm taking 75% of my data to become a training set, and the 25% my test set. That's the data I'm going to use to test my model. Ooh, okay. Let's go on. Now I'm creating the features. I'm taking the features and making them numeric now. because I want to run on top of this, I want to run just one algorithm, logistic regression. The simplest one, but very effective. So I'm concatenating all the fields, and I'm creating this vector assembler, which is just a transformer, right? It takes a bunch of columns and produces one new column of type vector that contains all the values from previous columns converted. Okay, now I'm doing the logistic regression estimator, which is just a reduce function, right? It will run on these feature vectors and will run the logistic regression optimizer and get results. Finally, I'm stitching this into the pipeline. So pipeline actually needs to get the stages in certain order. So it needs to prepare my fields first, and then at the end run the logistic regression. So that's why order here is very important. So I need to remember that too. And then I'm running the training. So great, I'm doing the cross-validation on the model with hyperparameter tuning, and this line, like train the model and compute scores, this is actually the line that does the model training, the effective model training. After this line, I can do whatever I want with the model now. I can save it, and I can score new data, and so on. So this is great because we've seen transformers and estimators, and some things are actually nice because we haven't mentioned anything about the old style coding such as MapReduce. There is no complexity of MapReducing anything. It's quite sequential set of steps. So we want to maintain the same ideas as we go. So the good parts, again, simple abstraction. We have transformers, say map, and then estimators is like a reduce. And then we have pipelines to stitch it all together. Pipelines are actually reducers too, so they're actually estimators. And then we have serialization of pipelines and transformers that allows us to save models. This is all implemented, so it's good. We don't want to reinvent the wheel here. PMML is baking still. You don't want to do it yourself, I guess. If you're brave, you can, I guess. Good implementations for estimators. So SparkML has a lot of cool stuff implemented already. And they care about quality, so they have a good test coverage. And I mean, I'm happy to use some code and don't reinvent the wheel. It's an all-in-one framework, so whenever you code, it's the prototype or explore your data, it's the same code that's being deployed. It's not like, okay, we're going to do Octave or R and then go write it in Pig Hive, whatever you use in your stack. It's here. It's the same Scala code that we all love and use. It has multi-language support, so happen to use Python. And it has a very healthy ecosystem. So this is the little graph of the issues for the last 30 days, closed and open. So you see it's a small gap. There is literally guys are working. Who is here from Databricks? Anyone from Databricks? Anyway, thanks for doing a great job. What else? So the not so good parts. Okay, the not so good parts. This list is not exhaustive too. And like, sorry, Databricks guys, but there is no type checking. Like I miss it. Like I built Spark code, and like each time I deploy it, I pray. Like it's so transformer estimators code are also way too open. Transformer code gets data set untyped, blah blah blah. Gets data set which is a typed data frame, but the interface right now it's a data set underscore, I missed it, but it's a data set of any type and it produces data frame. So I can do whatever I want. My transformer can erase all the columns because I can, and then everything down the line will fail. And it happens. So, and data frames are everywhere. They just everywhere, all around the code when you start looking into it. So it's easy to misspell column names, copy paste is horrible. No integration really with ML vector type, which most of the estimators use, and it misses a lot of RDD functionality. So RDD is the first type that Spark introduced. This is like a resilient distributed data set, and it's great. It has a lot of, it's mature, and it has a lot of functionality that we like. but it's just not there for data frames. When you say, for example, you aggregate a data frame, you get into this aggregated data frame that has maybe like 10 functions on it. We can't continue with this, so you need to constantly go back from data frame to RDD, data frame to RDD if you can, because RDD is typed. There is a lack of support for common I/O operations, so we need that, like join, aggregate, things we need. And schema algorithm definitions are all interleaved. We've seen that in the example. So can we do better? So we can definitely do better. So I'm going to show you an example of how we do that with Optimus Prime. So Optimus Prime is a transformation framework that we actively use for the last 2 years already. And it's currently in the V2 state. So we had a V0, V1, now it's V2. It's an internal kind of V, but it's getting happy. It's gonna get even stronger. So we want to have declarative syntax. We want to be able to argue on syntax better. We want to have your usability of I/O operations, and we want to separate features, transformations from data operations. We want to have it separately, even just for unit tests. You just want to define your transformation steps with your features and the engineer and everything, and then only then apply it to Spark. Maybe it doesn't have to be Spark. Maybe it's going to be Flink. Like, who knows? Ideally, you can also like replace your computation engine underneath. But it's very going far. So show me the code. Show me the source. You must. Yes, I must. I will. Here. So here's the same example with Optimus Prime. I'm doing the same solution for Titanic, but with Optimus Prime now. So for us, it starts from defining readers. So you would define some reader. It doesn't have to be in the same context, but you would define a reader that, in this case, it's a simple CSV reader that reads the CSV file. We have a bunch of pre-implemented readers that we use, like aggregated readers and conditional ones. So this one is very simple. It produces some Avro schema in this case. Then we want to define a response feature. So okay, I'm going to define my response feature. It's going to be some binary feature of survived, and I'm passing my extract method. It's going to be applied at some point, and I'm doing dot as response, my response feature. Great. Doing the rest for the rest of the features. Same thing. Have you seen any strings here? No, because there are no strings. Like, the only strings that we have are just the values. For example, equals survive. So obviously this logic will be a little bit more complex. But we actually deduct the feature names from the vals. This is the cool stuff behind the scenes. So it's basically what you see is what you get. If I define a variable age, this is the column name. I cannot define the same variable down the road in the same block. It's not going to compile because we get the uniqueness of the vals. How cool is that? So if I'm writing my code, I'm mixing multiple features into the context, and they will collide if anything overlaps, or they won't, and you're happy. It means that you're good. So great, we get at the compile time. No data frame collisions, no nothing. If you want to rename, call it like my age, great, it's going to be a new column. So moving on. Now I want to create family size. That's what I need to write. That's it. Like, because this is what it is. I don't want to define UDF in nothing. Okay. I want to fill missing. Great. I'm just going to create this operator. Fill missing with mean. Great. I'll do that. And for Southampton, I'll just do embark.fill missing with some value. Done. I'm done with my features. And then I'm going to make it a feature vector. Baking into the sequence, all the features I want, do as vector, I'm done. I have my numeric vector in there. So actually nothing of that still happens. Like, there is no Spark in the picture, right? And even here, nothing. We're creating this model selector that allows us to pass model parameters into it. For example, logistic regression and random forest and so on, and the classification. And then we stitch into the pipeline. The pipeline will rearrange and arrange the stages underneath. And only now we spin up Spark. And only now we're doing pipeline.fit. And we're creating the model, which we then use to do something with the test data, with a test reader. And then we can save it because we actually wrap around Spark. So we're using the same cool features of serialization. Just to summarize, everything is typed. Reader is typed, transformation, estimators, models, everything is typed. It's declarative. I think it's intuitive. It's like it's in our IDE. You do variable dot, and then it auto-completes based on type. Feature names are inferred from vowels, no misspells. Features are always unique in a code block, yay. We have a lot of common data operations that we did. And there is no data frames. I think this is, for me, this is the best line. I don't want to see data frames. Features and transformations are separate. Yes, they too. So what's happening behind the scenes? So we started by, okay, what's missing in Spark? Spark misses features, and it misses types and features. So we said we're going to define some features with some primitive types. So primitive types may be numeric, right, like a double, or text, which is an option string, and then categorical, map string to double. Okay, sounds good. Let's do this. And then we're going to do transformers, same transformers, but we're going to implement them in types now. So those are actually typed. I forgot to add the TUI. You will see it down the road. So features can be transformed with transformers. Okay, so features should have a method transform with, or the transformer should have a method transform feature, any of those. And then transformers produce new features. So when it's transform, they create new features that know their parent. Okay, great. Estimators, what do estimators do? Estimators can be fitted into becoming transformer, same as Spark does. So when I'm feeding a model, it becomes a transformer that you can transform a data frame with scores. And then we have pipelines. Pipelines are kind of a bit aside because they're also estimators, and they can also be fitted, but they also need data readers to operate. And that's where the actual I/O happens. So pipelines will initiate data reader, read the data in some format, and then they materialize features on this data, and then they become a transformer again. So you can do scores. So this is like the picture to keep in mind. So the only thing we mainly added is the feature and the data readers, and then we typed everything else. So they can all cooperate, work together. So these are our primitive types that we did. As I mentioned, numeric is double, so just shortcuts kind of. Because data scientists, they speak in the left words, I speak on the right words, and we want some common language to talk, so I'm kind of fine, let's do types. Key, binary, great. And then we define the type feature. So here's the type feature. This is the trade that we did. It took us quite a while to came up with. I kind of appreciate it's very compact. So it has an implicit weak type tag that we use to overcome the type erasure, and it's heavily used with our macros for a lot of things. The name of the feature is the name of the column in the underlying data set, or data frame. So when we actually materialize those features in the pipeline, this is the name that it becomes. Then we have some default value that's computed based on type. The origin stage means I'm a feature, where did I come from? What was the transformer that created me, or an estimator? It can be any stage. So some pipeline stage materialized me. And then I know my parents too. That's actually like important. Maybe it depends on, okay. And these are the features that are required for me to be materialized. This helps us to build those graphs of transformations. And then this is the function I was speaking before too. Transform with, that takes a stage and creates a new feature with a new type. So we have a type U here that is produced U, so it's always typed. We pass in the type everywhere. So some magic with macros. Say I want to write this. Val sibling supposes equals feature builder. So I'm just a helper to build features. And then I have to pass the name. So I don't want to pass the name. I wanted to infer from vowels. Can we do that? Yes, absolutely. So this is an example of how we did that. What? Submit again. Okay, sorry. This is not. So our macro takes take as a context, and then it tries to infer what's the defined eval name. If you want to know where I took that function, it's actually dig into the SBT code base. So they did amazing stuff on that. So because when you Google Scala Macros, you get nothing. So you need to actually go to GitHub and just search there, and then maybe get some cool examples, and then they have a lot of macros. So this is one of those. So this, for example, takes the val name and creates an expression of feature builder dot numeric blah 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 or apply, and passes in the type, and actually just rewrites the second line with the first one. It just passes the file name as a string. So underneath everything is a string, but it's hidden. It's hidden. Like, who cares? It works. I mean, it's great. Feature transformations with implicit classes. So we use implicit classes heavily so we won't have this annoying syntax, right? Siblings poses dot transform with blah blah new binary nullable and numeric transform with a plus function and a second feature, and then dot transform with another transformer with another function, and then one as a value. This is very, very annoying. So we want to do shortcuts. So we do implicit classes. And then we create a bunch of implicit classes for all our types. Like, okay, we want to do rich nullable numeric, and then this will have 250 operators that we support. Plus, divide, ampersand, like Boolean operators, fill, missing with mean. You've seen a few examples of those. So we're kind of expanding on that. So whatever data scientists need, we just add it. So it's very easy. All they need to do, they need to implement a transformer, and then we just stitch it into this thing. So very simple. Note, we also use macro here, correct, because we want to, I missed this because that macro is actually huge. To get the val name for this, I thought it's like, okay, I have only 40 minutes. Actually, I'm almost out of time, I think. Okay, where am I? Features and transformers. So this is like an example how it works underneath, just a visualization of how it works. So say I have this expression, and then this is the underlying data frame. So for each column, we specify a new feature, right? And then we apply the transformer, which produces a new feature, which we don't see in this expression, right? This is like an intermediate one. And then we do another binary transform with +1, which produces a new feature that becomes a new column. It does not materialize again immediately, but what we have from this expression is that we actually build this little transformation DAG. This is the most important thing. When we get into the end of the block, this is the thing that we hold in our hands. This is what users want when they engineer their features. They want to do some interactions between features, some normalizations, and then they get this DAG. From this DAG, we get the stages, and those go into the pipeline. This is we're gonna see it next. So what are pipeline stages? Pipeline stages are the same pipeline stages that Spark has. It's on the right, self-pipeline stage. This is Spark pipeline stage, but we added two types here, input features, output features. And then we do set input, get output, so we can stitch them together again. I hope you see the pattern already. And then we implemented the transform schema. This is a completely final override. It's like on the top class, we were able to do this. So I think I'm not showing that code because it's like 100 lines, but maybe less. But we're doing all those schema changes for underlying data frame when we apply this stage, which nobody has to remember doing anymore. So basically, for my binary transform, if I want to do plus, its input feature type will be a tuple of feature numeric, for example, and output will be a feature numeric, going back to our example. And then we did have to go and create those types for all the possible combinations. Okay, this one extends OP pipeline stage base, and it has one output feature, but has multiple. So it's something x to 1. And then we did, okay, this is the 1-to-1. This is the 1-to-1 mostly used. Take one column, create another column. But what if you want to have two columns? So this is for the binary one. two input types, one output type. How many combinations we have? As much as you wish. But it's super annoying. Whoever knows, and you obviously do Scala products, they only did to 22. So we kind of ended up on 5, but we want to have a lot. But if you have a lot, you're probably doing something wrong. So kind of, so we're still not sure we want to do that. And it's already annoying. It's like we have like 5, each time something changes, like all those classes, oh my God, I have to change a lot of things. So maybe there can be a macro to generate macros, to generate code for us. I don't know how that code will look like. I'm really scared. So here's an example of one-to-one transform. This is the most used one. Take a column, get a column. So a trait of a transformer, it now extends, you see we're mixing in our stage 1 and then the untyped SparkML transformer. But we have two new implicits here with the type tags that allows us to do a lot of magic at runtime. And then the user provides one transform function, and now this function is typed. So when the user operates with it, it just says, okay, here's the function, and I know the type of it. It's numeric to numeric, and do whatever you want with it. And we are creating the UDF underneath. But this thing is hidden, you see, so nobody kind of needs to know about it. Okay, and so on, and again, combinations here. Estimator example. I don't think I have time for this. Questions after. Yeah, sorry, I have a little bit more slides. So estimator example, this is the Spark estimator, but again, with types. So we're mixing in our stage with types. And now estimator has this feed function to basically become an unary model, which is just a transformer, another transformer. So I want to take an estimator, right? It's my model. I want to feed in a bunch of data. That's what I mentioned, data set, untyped data set. And I want to produce a transformer. So we're wrapping it all inside. I kind of stripped a lot of code here because we also handle the persistence. We're checking, okay, what's the persistence of this RDD? Should we cache it? Should we uncache it? And we do it all around this function. So basically, I stripped the code here and stripped the code here. I wasn't sure we can handle it with time constraints. But at the end, it produces this model. And this is what it is. Unary model is a class that extends a model and extends a transformer. It's typed. You just run it as a regular transformer. So, and this is the mechanics. Okay, so we have the data. That's what happens when we run our pipeline, when we run OP pipeline fit. We read the data, say it's RDD. We generate features, they become a data frame. This data frame then, okay, stays aside for a second, and then we take this transformation DAG from all the features that we want to use for our model. We do topological sorting on this because we want to have the correct order of application of those. And we know that nothing will overlap because we know the names are unique, so we're kind of good, okay? Even if we just add in columns, nothing happens inside the data frame. Nobody deleting columns because we own everything. Users only operate on functions, and those functions have no access to data frames. So I think this is like worth appreciating. Anyway, it's fine. So Spark pipeline, this is what we use underneath. So our pipeline uses Spark pipeline because we want to use the same serialization, same coolness thing that Spark has. So we just do a new Spark pipeline. We set our stages after we sort them, and then we feed in the data frame that we had, and at the end we get the model. So it actually works beautifully, and this model is inside our transformer that we produce. So going forward with Optimus Prime. So what's still missing? We're still working on adding common operations. So aggregator is a bit tricky. Joins are really tricky with like custom keys. How can I even identify keys, for example? Can we auto-identify keys? That would be great. We do have some aggregations that we do right now with algebra monoids. that we love, but maybe we can do a little bit better than this. We want to wrap around existing Spark code. So we actually, I didn't put it on my talk, but it's also like a separate topic, how we wrap around that. We want to have code gen for combinators. We want to do, again, code gen for macros, kind of scary for me. We want to do automatic feature engineering, right? Why are we even doing this? What if I just throw in the data and then it should just figure itself out? Like, okay, go figure out, sniff around my data and say which column is worth mentioning taking into the model, right? My example with Titanic, I handy-picked certain fields. Why can't it do it for me? Why do we need human intelligence to look into the fields? Why can't it even take all the fields, try all the combinations, and produce the best model? You say it's NP complete, yes, but who cares? I mean, I want it to work like this. So this is something we want to build further down the road. We want to do sanity checking, so just eliminate the features that are not good, and so on. So key takeaways for you guys: real-life machine learning is really hard. I don't know if you still didn't get it, but I'm going to repeat it. It's really hard. So unless if you just want to do some predictions, you can go fine with Spark and maybe even Python and Scikit, and you're good. But if you want to do it at scale as we do, you're going to have to invest a lot of time and a lot of thought into that. And we're this is the reality we live in. SparkML was great, needs type safety, I mentioned multiple times. We want to have intuitive syntax for our code when we develop it. We don't want users to remember special DSL, what this function called. I want to do dot completion. I want to do dot, and then in my IntelliJ or Eclipse, I want to see the list of functions that I'm allowed to do in this context. So Scala has all the relevant facilities. Just know to use it. Educate your teams, dig into Scala. There are a lot of good books available, and you are the gurus to do that for your companies. And then modularity and reusability is the key. Always remember, build the code so it will be reusable, not just copy-pasting code. You look into the core, what other concepts are missing. So we saw, for example, feature type is missing, so we went and implemented that, and then further implications followed. So try to look into the root of the problem. For further exploration, look on our website, einstein.com. Yes, we actually own this domain. Well, no, we rented it for 7 years. Prediction.io on Apache. Follow us with all the issues you have. We have a lot of great stuff there too happening. Prediction has a lot of templates for we already implemented, and again, once Optimus Prime is open source, we're going to start integrating in the templates into the Optimus Prime syntax. So, talk by Shubhanabar today is recorded. You can watch it later. And then there is a talk on Optimus Prime internals version V0, V0 mainly, yes, by Leah McGuire at QCon. QCon? Maybe not. But this is the link, so you're more than welcome. And then if you're really curious, really curious to know more, find me or my colleagues or email us or whatever. We're hiring. Okay, thank you.